Good day to one and all. I'm Swaparjit, and in this short talk, I will be discussing some crucial aspects of nonlinear optics. What is nonlinear in optics? To answer this, we have to understand what is polarization. We know that materials are made of molecules or atoms that are effectively neutral. Let us imagine there is an external electric field around the material. What happens now? The neutral or effectively neutral atoms and molecules polarize. We know that positive charges move along the electric field and negative charges move away from the electric field. If the electric field is strong enough, the electron clouds in the atoms get distorted. This in turn causes a dipole moment to generate inside the material. We say now that the material is polarized. The extent to which this distortion happens or the polarization happens is called susceptibility or polarizability of a material. This, of course, is purely a material dependent parameter. Thus, we say a material is linear when the polarization is proportional to the external electric field. On the other hand, in nonlinear materials, the polarization depends on higher order terms involving the electric field strength. Nonlinear optics is a wide area of study that involves the interaction between light and nonlinear materials. For the purpose of this talk, we shall restrict ourselves to just second order nonlinear optical effects. Let us first see the effect of a unimode electric field in a linear and nonlinear material. By unimode, we mean that the electric field has just one frequency component. The green graph here shows an electric field of wave vector 2 and frequency also 2. The blue graph shows the effect when it meets a linear material. Now, as we increase the nonlinearity, we see that the polarization term has increased by a constant, and also we can see that its frequency has doubled. This is known as the second harmonic generation. Now, let us see what happens when there are two modes. Now, the second mode given in orange has a higher frequency and therefore moves faster compared to the first mode. The net electric field is just an amplitude modulated electric field given in gray. In the linear medium, we see the same features but just scaled down. If we start increasing the non-linearity, we can see what happens. On squaring the electric field, we have a E1 squared, a E2 squared and a E1, E2 term. The E1 and E2 squared terms just give the second harmonic generation. However, the 2 E1, E2 term now gives us a field whose frequencies are added and another field whose frequencies are subtracted. This is the sum frequency generation and difference frequency generation. It should be understood that in a nonlinear material, all of these effects simultaneously happen. We can also try to understand the sum and difference frequency modes in terms of quantum mechanics. For some frequency, we can imagine two modes or two photons being absorbed by the material, going to a higher energy and de-exciting, giving an output photon whose energy is the sum of the input two photons. This is a spontaneous emission. On the other hand, for the difference frequency, two input modes of omega 1 and omega 2, which translate to two photons of energies h cross omega 1 and h cross omega 2, what happens here is quite interesting. The higher energy photons are absorbed by the atoms which get excited. Now, under the presence of the second photon of lower energy, this excited state undergoes a two-step de-excitation. This is a stimulated emission. To summarize, when two modes of electric field interacts with a nonlinear material, we have the second harmonic generation for each mode along with a sum frequency generation and a difference frequency generation. Remember, we saw that the polarization field increased by a constant. This increase by a constant term is known as rectification. What happens here is a static electric field is generated on the surface of the nonlinear. Now that we have been introduced to light matter interaction, we can understand what a parametric process is and a non-parametric process is. In a parametric process, the light matter interaction leaves the quantum state of the material unchanged. This in turn conserves the energy of the input modes of photon and the output modes of photons. In a non-parametric process, this is not the case. To realize these nonlinear effects, it is essential to choose the right kind of materials. A number of inorganic crystals, semiconductors, and organic materials have been identified over the years to show these nonlinear properties. The catch here, however, is non-centrosymmetric systems are the only ones that show second order optical phenomenon. For a centrosymmetric system, it would mean that if there is a potential experienced at position R, there must be an identical potential at position minus R about the center of symmetry. Therefore, in a centrosymmetric system, if the incident oscillating field at position R goes as plus E to minus E, by definition at minus R2 it must be plus E to minus E. But in a second order system, the polarizability is given by E squared, which would not change sign. The implication is thus non-centrosymmetric systems are the only ones that show second order optical phenomenon. In the case of inorganic materials, apart from the non-centrosymmetry criteria, crystals with appropriate birefringence are also a choice. Apart from birefringence, the chosen material must have required absorption cutoff, damage threshold to corresponding input laser power. Historically, quartz crystal was the first material used in the demonstration of the second harmonic generation of light with ruby lasers. Subsequently, many systems like perovskites, tungsten bronze type materials, iodates, phosphates, nitrates have also shown nonlinear effects. In all of these materials, the anion group has been identified to produce high nonlinear microscopic effects. It has been established through detailed studies that in general, borate compounds have better advantages of being nonlinear materials in the UV range. They possess transparency in the UV and deep UV regions. Due to their wide band gap, they also have high damage thresholds. In this concluding segment, let us talk about an exclusive quantum phenomenon of nonlinear materials called spontaneous parametric downconversion. Let us remind ourselves that a parametric optical process is one where light interacting with a medium leaves the medium's quantum state unchanged. In SPDC or spontaneous parametric downconversion, a high energy input photon called the pump photon on interaction with the material produces a pair of low energy photons called the signal and idler. To think about it, it is like a time reversed process of sum frequency generation. What makes SPDC a cornerstone effect is its extensive use in a plethora of quantum optics experiments, most notably in producing entangled polarization states in photons. For this, birefringent nonlinear materials like beta barium borate are used. Birefringent materials have refractive indices that depend on the polarization of the light that is incident on it. This produces what is called as the ordinary and extraordinary optical beams. Thus, by orienting the crystal in a suitable fashion, one can produce photons with the ordinary polarization and the extraordinary polarization. Should remember that the ordinary and extraordinary polarizations are orthogonal to one another. By adjusting the light cones of these photons, one can produce the polarization entangled photon states. To summarize this entire talk, we started with an introduction to nonlinear optical phenomenon such as second harmonic generation, sum frequency and difference frequency generation. We also tried to understand some of the material constraints of nonlinear optical materials. We finally ended with a brief introduction to quantum phenomena like spontaneous parametric downconversion. With progress in materials, newer avenues of research in the areas of quantum teleportation, quantum cryptography, and single photon generation are all made possible by nonlinear optical materials. Thank you.